It was you determine that you put a hot probe and a cold probe, right? And then you generate a large number of extra majority carriers, what I was looking. So in the case of N-type, you have electron that I showed, that electrons, so you have a diffusion going on from, because you have a large number of high energy majority carriers and they move from hot to they diffuse. And that gives rise to a current. And as a result, that if you have an N-type, this side you're losing electrons, so this becomes plus, and this becomes minus, right? So the current flows in this side. And the same thing happens if this was a hole, a P-type. When holes are majority carriers, they will leave the hot probe, go towards the cold. So that was the answer, that N-type, the electrons flow from hot to cold, right? And therefore this region becomes plus. The current goes that way, and in the hole it is opposite. Okay, then the next question was that why the oxidation rate is different when you are changing the ambient from wet to dry, or when we are changing the crystal orientation from 100 to 111. So basically the answer is that, I pointed out a few times that you have a higher solubility, right, which is the C0 for the H2O, and you have a higher diffusivity. Remember, the activation energy for the H2O migration is 0.72, and for the oxygen it is more than 1 eV. So if you remember that plot that we talked about, so there are two reasons. You have higher solubility and you have a higher diffusivity. That was the answer. And because of those two reasons, H2O moves through the SiO2 much faster. So that's the answer for that. And then what happens when you switch the orientation? So orientation 111 has more atoms per centimeter square. It has higher atomic density, so you have more targets of silicon when oxygen or H2O is coming. So you got more targets, means you're making much more SiO2. So oxidation rate is higher when you use 111 versus 100. So that was the answer for that one, right? It has more targets, okay, and therefore it's faster oxidation, and therefore the rate is higher for 111 over 100. Then give two reasons for higher resolution. In the case of projection printing, why it is higher resolution, and why. Well, what are the two disadvantages? So I was looking for two. So basically, the most important thing, and we talked about, was that in projection you use a reticle which is 10 times larger, right? So you're making a reticle 10 times larger, means that all the openings are 10 times larger than the actual chip size, and then you demagnify. But having a larger opening means you have less diffraction, right? Because opening is much greater than the wavelength. So diffraction happens when opening and wavelength become comparable. But since I'm using a larger opening and then I'm demagnifying it, so there is less diffraction, and that was one reason for the resolution being better for projection. The second is you don't expose the whole wafer. You are exposing one chip at a time, so you are scanning. It's a scan, step and repeat. So when you are looking at a very tiny area, there is a variation in the wafer topology. Since you are looking at exposing a tiny area at a time, chances are that you don't have huge roughness variation. That means your depth of focus would have to be very large if you expose the whole wafer, and the whole wafer can have a much bigger variation in the roughness because it's a large area wafer. But if you do only tiny area, chances are that topology variation is not that great in a tiny area. So that was, so a smaller area scan, which is a step and repeat, it improves the resolution because of insensitivity to topography. And the second is basically, the most important one is you have the luxury of making the gaps of the holes much larger, so light can go straight through it without getting diffracted. The two disadvantages that most of you got all right. One is that it's very expensive and it is very slow because you are exposing one chip at a time on a wafer, not the entire wafer. So it has a lower throughput and it is more expensive, right? And if you wanted, there is another disadvantage is that it's more sensitive to defect because it's the same reticle you are using for all the hundreds of chips. So if there is one defect in that reticle, all the chips will be having the same defect. So that's the third disadvantage of that, right? So it's cost, right? Lower throughput, right? The third, I don't know why some of you started talking about things about what may happen in the lab because of it. I'm just asking what are the three reasons your actual profile may differ from analytical. And if you remember, I said so many times that it's things like these I would ask in the exam. And there were 4 things we talked about in the lecture which can make your diffusion profile different, which is we calculate it analytically, right? Which means you use a diffusion equation where you assume D was constant and set at any time. That may not happen, that you have a constant D all the time. So what changes D is, remember 4 things we talked about. I asked for only 3. One is that if N is greater than Ni, you have charged vacancies, and that creates an extra path for diffusion. Okay, and the other way to look at it, that when N is greater than that, you basically have Fermi level is greater than EI, and if you didn't have to write that, but if you remember that raises the total number of vacancy from CI exponential of EF minus EI. But the main thing is that when you got doping is greater than Ni, in addition to the intrinsic vacancies, you start creating vacancies that are charged. So now you've got total vacancies are much greater, your normal, neutral vacancies and charge, and they both assist in diffusion. So you have another channel for diffusion so that your effective diffusion is greater than the diffusion when there were no charge vacancies. So that is, but in our analytical calculation, we didn't account for that. We just assumed D was constant, independent of what is the doping or the position. We said it's constant. And that was a major assumption, which is not very seldom it actually happens. We normally, you got some profiles which are very high doping, so you run into this problem. So that's why you may see some difference. And so your diffusivity actually becomes higher than if this was not the case. The second, we talked about that you are doing diffusion at such high temperature, right? So all the dopants are ionized. So phosphorus is P plus and the electron is ionized. Now they both can move, but electrons can move much faster. And so if electrons are here and the P plus is here, there is an electric field between the negatively charged electrons and the ions. So wherever atom is sitting, it's ionized, right? But now they both will move, but this guy moves much faster. So this is now negative electron and you got positive ion. So there is an extra attraction or a field that drives the ion. So this is called field assisted diffusion because you got a charged situation here, electrons and phosphorus, this is an example, that creates electric field to accelerate the dopant diffusion. The third thing we talked about, that if you are doing driving during the oxidation, during the drive-in, that oxidation injects silicon interstitials, and they knock out the atom from the dopant atom from the substitutional site to interstitial, where they can move much faster, like phosphorus. So it can increase the diffusivity because it is not going from substitutional site to substitutional. Part of the time it is being kicked out and it becomes interstitial. So this happens, it can increase the diffusivity if the atom like phosphorus can move very fast, but it can also decrease, like if you have arsenic cannot move interstitial to interstitial. So because of this injection of silicon interstitial, your diffusivity will be different from what you used in the equation, because we didn't account for this phenomena that it is partly substitutional, partly interstitial. And then fourth thing we talked about, that there is a segregation coefficient at the silicon dioxide interface. So when it distributes, if you got phosphorus, it piles up at the interface. If you got boron, it depletes at the interface, right? Because of the segregation coefficient has to be met. So those are four reasons. So I just wanted to, basically one reason was that D is not independent of the position or the concentration. That's number one. Second is there is a field assisted diffusion also happening because of the ionization of dopant. And the third is, if the silicon interstitials are being injected, they knock out the dopants from substitutional side to interstitial, and that can change the diffusivity, because interstitial diffusion is different from the substitutional. So those were the key reasons, and if you could have just gone straight to the point, but I still gave, you can see I'm always very liberal in giving points. You can see even if you wrote something which is remotely connected, I gave in some point, right? So and as told you, if you look at the grading I did, I'm looking for ways to give you points. So in some of you guys started writing, oh, in the lab, if some temperature, something happens, or something, the time or something related to what happens in the lab, mistakes. So I still gave 1 or 2 points for that, because, but that's not the question. The question is why you're analytically calculating where D is constant, but there are 3-4 things that can change the D that you are using in the equation. So that was the question 1. So basically simple answers were there. In the projection printing, basically because you are using 10x reticle and scanning a small area. Those are the reasons why it has better resolution, correct? Okay, then oxidation was very simple, that H2O molecule moves much faster through the oxide, and solubility is higher. So you got more to start with, which is solubility, and faster movement. So obviously you will have a faster growth rate with H2O. Okay, so that was problem number 1, which okay, problem 2 I thought was very straightforward, and a lot of you got this all right. So I just gave a little picture, and I said if I'm doing an oxidation here, okay, and gave you one condition for oxidation, that the whole wafer is put inside a furnace at 1000 degrees with steam oxidation, okay, for 1 hour. Tell me how much of the oxide, what would be the final thickness of the oxide in these 3 regions, right? So some of you just somehow remember that there is no oxidation through nitride. You remember when we were talking about the low-cost process, you put the nitride, right, and then you oxide the middle. You do oxidation, if you remember this question, the next question, when you do low-cost process, you cap it with the nitride, right, and then when you oxidize it, there is no oxidation taking place here. And this is why you can line it up very nicely. So when you have that's why nitride cap is put. So when you are doing the oxidation in the